In the fast-paced world of algorithmic trading, designing effective trading algorithms is critical. This process requires a blend of financial theory, data analysis, and programming skills. In this video, we'll explore the key considerations and methodologies involved in building robust and efficient trading algorithms. By mastering these principles, traders and developers can leverage automation for superior trading performance. Phase 1. Defining the trading strategy. The first step in designing a trading algorithm is defining a clear and well-thought-out strategy. A trading strategy includes a few key components. 1. Market focus. Which financial instruments or markets will the algorithm target? This could include equities, forex, commodities, or derivatives, and the choice of market will influence the design of the algorithm. 2. Trading style. Decide on a trading style, whether it's day trading, swing trading, or trend following. Each style brings its own requirements and constraints that will shape the algorithm's design. 3. Entry and exit criteria. Define the conditions that trigger the algorithm to enter or exit trades. This could involve using technical indicators, price patterns, or other quantitative signals. The criteria must be clear, actionable, and consistent with the overall trading strategy. Phase 2. Selecting models and techniques. Once the strategy is defined, the next step is choosing the right models and techniques for the algorithm. 1. Technical indicators. You can use indicators like moving averages, relative strength index, RSI, and Bollinger Bands to identify trading signals and analyze trends. 2. Statistical models. You might implement models such as linear regression or ARIMA to forecast price movements based on historical data. 3. Machine learning. Advanced techniques such as neural networks and decision trees can help your algorithm detect complex patterns and adapt to changing market conditions. Phase 3. Coding the algorithm. Now comes the technical part. Coding. This step transforms your strategy into a functional program capable of executing trades. 1. Programming language. Popular languages for algorithmic trading include Python, C++, and Java, each with strengths. Python is favored for its ease of use and vast libraries for data handling. 2. Data handling. The algorithm needs to manage data efficiently, integrating real-time data feeds and processing information rapidly. 3. Execution logic. The code should include logic for trade execution, ensuring fast and accurate order placement while accounting for slippage. Phase 4. Incorporating risk management. A well-designed algorithm must incorporate robust risk management to safeguard against significant losses. 1. Position sizing. Determine the size of each trade by considering factors like account balance, risk tolerance, and market volatility. 2. Stop loss and take profit orders. Use these orders to automatically close positions, protecting profits or limiting losses. 3. Diversification. Spread risk across different assets or strategies to minimize the impact of adverse market movements. Phase 5. Backtesting. Methodologies and best practices. The primary goal of backtesting is to identify how well a strategy would have performed in the past, providing insights into its potential future performance. In this section, we will explore the methodologies and best practices associated with backtesting, offering a comprehensive guide to effectively evaluating trading algorithms. Methodologies for backtesting. 1. Historical data selection. The success of backtesting depends heavily on the quality and relevance of the historical data used. First, consider data granularity. Intraday strategies require minute-level data, while longer-term strategies might need daily or weekly data. Next, ensure data quality by using clean, accurate datasets free from errors and anomalies that could distort results. Lastly, account for data scope. Use a comprehensive dataset covering various market conditions, such as different economic cycles and volatility regimes, to ensure the strategy performs well across diverse scenarios. 2. Strategy simulation. This step involves applying the trading algorithm to historical data to simulate its performance. It includes simulating trade execution while considering slippage and transaction costs, which ensures realistic performance insights. The evaluation focuses on performance metrics like total return, Sharpe ratio, and maximum drawdown, which highlight profitability and risk-adjusted returns. Finally, adjust parameter configurations cautiously to avoid overfitting while optimizing the strategy. 3. Out-of-sample testing. This involves validating the algorithm on data not used during development to assess robustness. Key steps include the train test split, where data is divided into training and testing sets, and forward testing, which applies the algorithm to live markets, providing a real-time performance evaluation. 4. Walk-forward analysis. The process includes rolling windows. Divide the historical data into rolling windows, where each window represents a period for training and testing the algorithm. The algorithm is re-optimized at each window to adapt to new data. Evaluation metrics. Assess the performance of the algorithm across different rolling windows to evaluate its consistency and adaptability. This approach provides insights into how well the algorithm performs over time and under varying market conditions. Best practices for backtesting. To prevent overfitting in backtesting, prioritize simplicity by using straightforward models and avoiding unnecessary complexity. Simple strategies tend to be more robust and less prone to overfitting. Additionally, apply regularization techniques like penalizing overly complex models or employing cross-validation methods to improve algorithm performance and generalization. Further accurate backtesting, incorporate realistic assumptions to reflect real-world trading conditions. Transaction costs. Include commissions and bid-ask spreads to evaluate net performance accurately. Slippage. Account for price differences between expected and actual execution. Validate the results using multiple metrics. Risk-adjusted returns. Use ratios like Sharpe or Sortino to assess how well the strategy compensates for risk. Drawdown analysis. Examine maximum drawdown and recovery periods to gauge potential losses. Lastly, document and review. Record keeping. Keep detailed logs of data and parameters. Peer review. Get feedback from experts for additional insights. Phase 6. Avoiding overfitting and data snooping. In algorithmic trading, avoiding overfitting and data snooping is critical for developing effective strategies. Understanding overfitting. Overfitting occurs when an algorithm becomes overly tailored to historical data, capturing random noise rather than meaningful patterns, which results in poor performance on new data. Common causes of overfitting include excessive complexity, where models with too many parameters capture noise, and insufficient data, leading to the model learning from outliers. Detecting overfitting. Detecting overfitting involves comparing an algorithm's performance on training data versus unseen data out of sample. Key techniques include using performance metrics to spot significant disparities between training and validation results and employing cross-validation methods like K-fold cross-validation, which tests the model iteratively on multiple data subsets. Mitigating overfitting. Mitigating overfitting involves simplifying the model by reducing parameters, using feature selection, and implementing regularization techniques like L1, lasso, or L2, ridge. Increasing the amount of data for training can also help by including diverse data from various market conditions and time periods. Incorporating synthetic data can further enhance the algorithm's robustness, ensuring better generalization and performance in live market environments. Phase 7. Understanding data snooping. 1. Definition and risks. Data snooping, also known as data mining bias, occurs when a model is excessively tested on historical data in an attempt to find patterns that are not genuinely predictive. This repeated testing can lead to spurious relationships being identified, resulting in an overestimation of the model's performance. Key risks associated with data snooping include false discoveries. Patterns identified through extensive data testing may not hold in live markets, leading to strategies that fail to deliver in real-time conditions. Reduced generalization. Over-testing on historical data can lead to algorithms that do not generalize well to new data or changing market conditions. 2. Preventing data snooping. To avoid data snooping, it is important to adopt practices that ensure the integrity and validity of the trading strategy. Strategies include pre-specified models. Develop and test trading algorithms based on pre-specified models and hypotheses, rather than iteratively searching for patterns in the data. Rigorous validation. Use robust validation techniques, such as out-of-sample testing and forward testing, to assess the algorithm's performance on data that was not used during the model development phase. 3. Transparent methodology. Maintaining transparency in the methodology used for developing and testing algorithms helps to prevent data snooping. Documenting the process, including the rationale behind model selection and parameter choices, ensures that the approach is reproducible and less susceptible to bias. By following these methodologies, traders can develop trading algorithms that are both robust and reliable, avoiding common pitfalls such as overfitting and data snooping. The key is to maintain a balance between model simplicity, data quality, and rigorous testing to ensure success in live market conditions.